Let's jump right into this explainer. Have you ever wondered what happens when we take our everyday scientific intuition and throw it directly up against nature's most extreme laws? Today, we are going to logically analyze a series of totally bizarre scientific hypotheticals. We'll be testing exactly how physics, thermodynamics, and even our own squishy human bodies behave under seemingly impossible conditions. Get ready, because what you think you know about how natural phenomena work, well, it might be completely wrong. Let's kick things off with a classic. Imagine we could magically conjure up a planet-sized bucket of water and just dump the whole thing directly onto the sun. Would it put out our star and leave the Earth frozen in the dark? You know, everyday intuition tells us that water puts out fire, but does that logic actually hold up in outer space? So let's look at Section 1, Putting Out the Sun with Water, focusing on cosmic physics and nuclear fusion. Here is the thing. The normal fires we see here on Earth, they need oxygen to burn. Water puts them out by cooling down the fuel source and smothering that oxygen. But if we analyze the natural phenomenon of a star, the scientific reality is that the sun is not a fire at all. It is actually a giant cosmic reactor, powered by nuclear fusion, and the specific fuel it runs on is hydrogen. Now, what exactly is nuclear fusion? Basically, it is this staggering natural process where hydrogen nuclei literally smash into each other and fuse together under just unimaginable pressure and heat. Now think about water for a second. What is its chemical makeup? It is fundamentally composed of hydrogen and oxygen. So, logically, pouring water on the sun leads to a completely catastrophic outcome. First off, you wouldn't be putting it out. You would actually be feeding the reactor with a massive amount of new hydrogen fuel. Because of that, step 2 kicks in. The sun's mass would increase tremendously. And what happens to physics when you drastically increase mass? Step 3. The sun's gravitational pull gets way stronger, ripping the Earth out of its normal orbit and pulling us in closer. So Earth wouldn't freeze. Instead, we'd get absolutely scorched by the multiplied heat and crushed by the intense gravity. No way around it. All right, let's move to Section 2, falling through the atmosphere, where we'll logically look at thermodynamics and buoyancy. Picture this. You jump out of a plane, but you only have an empty balloon and a helium tank. Could you theoretically inflate it while falling and survive the drop? Let's break this down strictly through the physical laws of buoyancy and gravity. 16. That number right there is the whole problem. 16 feet is the absolute minimum width a balloon needs to generate enough buoyant force to even start slowing your descent. One little helium tank? Yeah, not even close. But the bigger issue here is time and weight. Trying to inflate a massive 16-foot balloon midair would just take way too long. And worse, carrying that heavy metal helium tank makes you plummet at terrifying speeds. You literally wouldn't start floating until you dropped the tank to lose its dead weight. So realistically, you'd need thousands of miles of freefall just to finish inflating it. And at those extreme altitudes in the upper atmosphere, you'd pass out from a lack of oxygen long before the balloon even opened. Since we are already falling from extreme heights, let's talk about another physical phenomenon. Air resistance. This is the friction caused when a fast-moving object smashes into air molecules, generating extreme heat. So how can we apply this? Well, what if we dropped a raw steak from space? Would this intense natural friction cook it perfectly before it hit the ground? Let's logically analyze how the meat reacts to the atmosphere. If we drop a steak from 155 miles up, it is falling at a blistering velocity. The leading edge of that steak is violently compressing the air in front of it, generating a huge shockwave and thousands of degrees of heat. You might think it cooks perfectly, but no. That extreme heat instantly sears the outer layer into a charred crust, which then flakes right off, burning the next layer and peeling away exactly like an onion. Meanwhile, the upper atmosphere is blasting the trailing side of the steak with freezing, icy winds, which keeps the inside completely raw and cold. So the physics here leave us with a steak that is totally incinerated on the outside and frozen solid on the inside. Let's dive deep into Section 3, the terror of ocean pressure, focusing on hydrodynamics and enclosed spaces. Imagine this absolutely terrifying scenario. You wake up trapped inside a sealed glass coffin, sitting on the bottom of the ocean, and the only tool you have is a hammer. The psychological panic would be intense, right? You have no idea how deep you are or how much oxygen you have left. Every single breath burns the clock. Do you smash the glass to try and escape? This is where the sheer force of nature plays a deadly game with you. If you are down at an extreme depth, the external water pressure is so massive that shattering that pressurized glass will cause the water to rush in with an instantaneous, crushing force. It would end your life in a fraction of a second. But if you happen to be at a shallow depths, breaking the glass is literally your only chance to float up to the surface and survive. That hydrostatic pressure acts as a totally invisible, lethal variable. Swinging that hammer is a literal gamble against the cold, hard laws of hydrodynamics. Moving back to dry land, Section 4, Laws of Motion and Human Bodies, looking at kinetic energy transfer. We have all seen a Newton's cradle, right? That classic desk toy with the swinging metal balls that clack together to transfer energy. But what if we replaced those solid metal balls with actual human beings? Would this biological pendulum work the same way and cleanly transfer that kinetic energy? Let's logically break down why this is guaranteed to fail mechanically. Those metal balls only work because of their high elasticity and rigidity. They compress for a tiny fraction of a second and then transfer the kinetic energy flawlessly, popping the last ball into the air. But human bodies, we are soft. Our squishy biological mass absorbs shockwaves and kinetic energy instead of passing it along. The people in the middle wouldn't transfer the motion, they would take the absolute full brunt of the impact, suffering severe, crushing injuries. And here is a wild fact. Even if we put everyone in rigid metal armor to mimic the steel balls, the bones inside would still break. The energy would just dissipate into tissue destruction before it ever reached the final person. Physics, it turns out, is incredibly unkind to soft bodies. Finally, we arrive at Section 5, the boiling water metaphor, examining how matter reacts to extreme environments. 20 minutes. That is the exact amount of time we are using for this simple yet incredibly profound thermodynamic experiment. We are going to take 3 vastly different items and subject them to the exact same extreme natural condition, sitting in a pot of aggressively boiling water. Our test subjects? A potato, an egg, and a handful of coffee beans. Now, let's logically analyze how these different materials react chemically and physically to the exact same environment. The tough, hard potato hits the boiling water, and the intense heat immediately starts breaking down the molecular bonds in its starches, turning it completely soft and limp. The egg, which started out fragile with a liquid inside, undergoes protein coagulation thanks to that extreme heat, and it hardens solid. So the extreme environment is identical, but the physical transformations are completely opposite. But then, look at the coffee beans. They do something absolutely incredible. They don't just endure the heat. They chemically interact with it. They alter the extreme environment itself, transforming that boiling water into something completely new, rich in flavor and aroma. And that brings us to the end of this explainer. We have logically broken down how the strict laws of physics and thermodynamics govern everything around us, from the massive fusion reactions in stars to the crushing, terrifying pressures of the ocean floor. And just like matter in nature, it is our physical and chemical reactions that determine our outcomes. So when the heat rises and the pressure is on, how do you react? Do your structures break down like the potato? Do you harden up on the inside like the egg? Or do you use the energy of your environment to adapt, chemically alter your surroundings, and create something entirely new, like the coffee bean? In science, just like in life, the outcome always depends on how you handle the pressure. Thanks for watching, and we will see you next time.